In our multi-view drawings, a point in space is depicted as a plus or a cross, unlike the normal dot that we are used to representing it as. We will begin this video by discussing hidden lines. Hidden line is a thin line and consists of equally spaced small dashes. At the end of this section, we'll discuss common mistake and conventions with respect to hidden lines. And now I'll show you some common features that are hidden and how they are represented in our drawings. You'll now be shown rotating isometric views and a view in which a hidden feature is observed. Now we have some conventions regarding the representation of hidden lines in your drawings. There's no need to mug these up, just have these with you when you're drawing the first few times and you'll slowly start to remember them. Now we'll discuss a little bit about center lines. It is also a thin line and it generally indicates the center of circular features or the axis of solids of revolution. It has alternating long and short dashes. Here we see the representation of center lines on a cylinder. Now a hole is 9 times out of 10. A simple hole is basically represented as a negative of a cylinder, so it will have the same center lines as depicted in this diagram. So it's good to have this diagram in your mind when working with cylinders. Now we see the representation of center lines on a semicircular feature. This part is a small exercise for you guys. I'd like for you to identify the circular features and draw the center lines for those features. I'll be providing you with the multi-view of this part. The extruded cut is referred to as a slot here. You can pause the video right now and try to fill in the center lines. I'll be uploading the answer in the next slide. Now I'll show you how to visualize, transfer / represent ellipses and other circular features in your drawings. It's good to have a conic section visualization of these relatively circular features. Here is a video or a graphic showing you basically the definition I had given in the previous slide of an ellipse basically being a circle with one of its axes lengthened or foreshortened. Here you can see that the feature or the line seen on the left in both the top and bottom diagram is a circle, but when the circle is observed using a parallel plane of projection to its face, we observe a circle. But when the circle is inclined, or that same plane of projection is now no longer parallel to the face of the circle, we observe the same circle as an ellipse. Saying the plane of projection is parallel to the face of the circle is same as saying the lines of sight are perpendicular to the face of the circle. Now I'll show you the same situation in a 3D animation so that you can have a better visualization of the case where the circle is observed as an ellipse. You can see that both the features inside the box are circles, but when viewed through certain planes of projection, one of the circles is seen as an ellipse. Now we move on to the case where an ellipse is observed as a circle. We can clearly see that the top face of this cut cylinder is an ellipse. But when this cylinder is observed from a plane of projection that is generally referred to as the top plane, we observe a circle instead of an ellipse. We now have the isometric view, the front view and the right side view of an object. The curved face in the isometric view introduces a lot of confusion for students. We have the front view viewed from that angle, the right side view viewed from that angle, and the top view that we are supposed to get viewed from that angle. Front, right, top. I see that in the right view given to me, the circle is seen as, the feature is seen as a semicircle. So to make this curved part or semicircle easier to transfer into other views, I divide my curve into equal number of parts. To do that, I get the number of parts and divide the angle 180 by the required number of parts, and then I transfer all these points into the front view. When all the points of the curved face are transferred to the front view, I now will draw parallel projectors from the front view to the top view, and the similar process using miter line to draw parallel projectors from the right side view to the top view. I have drawn in my folding lines before I draw in the projectors. I haven't really used a set square or two rulers to draw parallel lines, which is bad on my part since I'm trying to give you an idea of the most optimum way to carry out your drawings. Anywho, I have a general idea of what the top view is supposed to look like because of the isometric view given to me. Now I have the features transferred from both the front and the right side view and try to locate their intersection in the top view. I now draw in the curve using a free hand. You see why dividing that circle was so important. My free hand is not an accurate representation of the curve. To get a more accurate curve, I'd have to divide the semicircle in the right hand view into a greater number of equal parts. I now draw out my top view with a sketch pen so that you have a better idea of what it looks like. That looks roughly correct with respect to my isometric view, and I have confirmed the transfer of all the features from my top and right view. This is generally the process that you must go through when you're transferring ellipses, parabolas, any of those conic sections. It generally requires the division of the curve into multiple parts, especially if it's seen in an adjacent view as a circle. I hope it was easy for you to visualize the intersections I got in the top view. See, the right side view is basically just the curved face, and I know that the curved face is represented along the inclined edge in the front view. So now I know what each projector represents in my given views. We'll see various holes found in technical drawings with their top and front views and the various dimensions used to represent them. We have the through hole, blind hole, and counterbore hole. Through hole is one that extends throughout the part. A blind hole extends partially through the part. A counterbore hole is used to make a bolt flush with the surface of your part. Now then we have the countersunk hole. A spot face hole is just a very small counterbore and a threaded hole. Any hole that requires screws to be inserted into it needs to be threaded. A countersink is generally used to make the screws flush with your surface. A fillet is any edge or corner of a part that is smoothed out. If it's on the interior, it's a fillet. If it's on the exterior, it's a round. It will be clarified using this diagram. Uh, Machine finished parts are generally not smooth, so fillets and rounds generally occur on parts that are cast, forged, or any plastic parts that are blown into molds, etc. This figure is used to clearly illustrate the difference between a machine finished part and a part that has a fillet on it. To draw or not to draw. Working with fillets is tricky because sometimes they represent a smoothed out edge that was technically a change of plane edge. So the first question that comes to your mind is, should you draw that edge or not in your drawing? In the slide that follow, I have shown some examples of why it is important to draw that change of plane line. If that change of plane line that represents the fillet is not drawn, there is a loss of information and it makes your drawings incomprehensible. You can compare and contrast the yes and no situation in the upcoming slide to visualize what I'm saying. Observe how, if you were given the top view as the one represented in the row labeled as no, you'd have no idea what the object looks like in the top view.